in all cases. And then the CPU time shown here would go like n times the same constant squared. So it really is proportional to n alone. Although I've drawn a figure showing an increasingly longer body here, in fact you'd more likely be studying the same body with a coarse mesh and then a finer mesh. So this is just artistic license. And the same will be true now in our two-dimensional problem studied next. Consider a rather coarse mesh here at the left, and then increasingly finer meshes leading to larger problem sizes. Now, the side of this block of nodes here would vary as the square root of the area. In other words, the square root of n, since the number of equations varies as the area there. And the bandwidth goes pretty much as the side dimension, because you have to number along the side until you can come back again, and that causes the largest distance. So we will put square root of n in here in the bandwidth dependence, and then find that your total CPU time goes like the number of equations times the bandwidth squared, and totally as the number of equations squared. Now let's turn to a three-dimensional problem. Here we have a small cube with a certain mesh density, and then it's increased and increased even further. To figure out the bandwidth of such a system, and referred to the number of equations, we would have to realize that a side of this problem would be proportional to the cube root of the number of equations, which is proportional to the volume. The bandwidth, because you have to number across an entire face before you return to the second row of elements, would vary like the area of this element. In other words, the bandwidth goes as n to the 2/3. We then can calculate the CPU time required is n times n to the 2/3 quantity squared, and we'll get n to the 7/3. So this would be the way that a increasingly refined mesh of a solid body would cost as you increase the number of equations. Several years ago, I did a series of problems with the code SAP6. That was a very popular code in the universities. One thing I really liked about the code was that it broke down the costs of the various phases of the solution and presented those to the user at the end. I've gathered some of those cost items here. They include the model input, the element stiffness generation, the load input, assembling the stiffnesses, decomposition, and then the forward and back substitution. It's interesting to see how these numbers change as you go from a small problem to some larger size problems. Now, the small problem was a static problem with 4 load cases, and it's dominated by putting the data in and some introductory massaging, and then the forward and back substitution at the end. A medium-sized problem would be one here, a static problem with several load cases, 1,300 degrees of freedom, actually pretty small by today's industrial standards, in which already the data entry and the introductory preliminaries are not very expensive, and already you're up to 78% of the cost in the decomposition and only 4% in the forward and back substitution. Lastly, when you come to 4,800 degrees of freedom in a dynamics problem that was a modal analysis, it required 6 modes. This also uses the forward and back substitution and the decomposition, so it's actually related, and I guess you just have to take my word for that. The thing I wanted to point out was that the introductory portion of the solution becomes less and less a factor. The decomposition is growing even further to 85%, and then forward and back substitution is dropping out also. Now, today's problems commercially are averaging 35,000 degrees of freedom, and the decomposition becomes a large part of the total solution time. Our first problem in the problem session will have to do with a handmade bandwidth optimization for a two-dimensional structure. Here I'm asking that the attendee look at this figure. It's a sheet metal structure with a triangular hole in it, and that you number this given mesh so as to give the minimum bandwidth. Now, I ask for detailed notation. I might work it out in compact notation, but ultimately we've got to tell how many physical degrees of freedom there are in the bandwidth. In solving this, I actually tried several patterns for nodal numbering. And of course, nodal numbering is the key when you're working with bandwidth. There are 11 nodes, and if possible, you'd like to number through the thin direction. Well, for me, that might mean passing in this sort of general way through the body, and you can see that I've done that with node 1, 2, 3, 4. 5, 6, 7, 8, and then 9, 10, and 11. And when I've done this, I can make the difference in each element in the red numbers here. That is 3 for that element, 2 for this one, and then there are a lot of them with 4s. It's pretty hard to get past that, and then another 2 up here and a 3 here. When you see this, you can see the odds are you're not going to get a minimum bandwidth of 3 because there are so many of the 4s here. 1, 2, 3, 4, 5, 6. I don't want to get into generating any small rules for this because we just mean this to be a hand exercise and nothing formal. But the numbering scheme that I've chosen really is the best you can do, and the largest D is 4. You add 1 to that. There are 2 degrees of freedom per node in a two-dimensional plane stress problem like this, and that adds up to give a bandwidth of 10. Remember that in our notation for these real symmetric matrices, this is literally the semi-bandwidth, but everyone will call it the bandwidth. Now let's do a bandwidth problem where there are moments involved. I'm proposing that you study a wooden stair railing here, which is firmly embedded in the wall at the right end, and these spindles are firmly embedded in the floor at the bottom and into the rail itself at the top, such that all of those joints are considered to be perfectly fixed joints. They're fully joined with moment continuity. Now the question is, when a human walks along that rail and pushes with their hand downward, and if you consider this as a two-dimensional frame structure, what is the bandwidth of the original set of equations without the constraints added? That's part A here. And of course we want you to explain your reasoning. Then, after applying the constraints, which are single point constraints at the wall and floor, what is the minimum bandwidth of the reduced set of equations? And explain your reasoning again. Now we're modeling a frame in 2 dimensions. Each of those joints will have 3 degrees of freedom. There will be 2 translations and 1 rotation. One of the members coming into that point will possibly be carrying that translation as a shearing load, and the other perhaps as an axial load. So if we start off with the original model shown here, then I'm showing the 3 degrees of freedom per node. If I do an optimum numbering sequence for the nodes, I might start at the bottom here, move up to the left vertex, and then there would be a spot, some general spot, where the degrees of freedom where the hand pushes down would have to be modeled, and then perhaps another beam joint, and then at the floor another joint, and so on. The largest difference in nodal numbering in this case will only be 2, because if we number 1, 2, 3, 4, 5, 6, then we never have up above more than, for instance, in this member, 6 minus 4, which is 2. So I do show that here. We can then use the formula for bandwidth. That bandwidth is the maximum difference in numbering plus 1 times the number of degrees of freedom per node, which is 3, and the maximum difference was 2. So you get a bandwidth on that original model as 9 in what I call detailed notation, which means you're including all physical degrees of freedom. On the other hand, if you constrain now those degrees of freedom that are clamped at the floor, which would have been down at this level, and at the wall, which would have been at the right, then you are left remaining only a line model which has nodes distributed on it as shown. This time you would logically number your nodes 1, 2, 3, 4, merely from left to right as an optimum sequence. And then in this case, the biggest difference would be 1. So your bandwidth would be 1 plus 1 times the 3 degrees of freedom per node, leading to a bandwidth of 6 in detailed notation. This stair railing was actually something that my wife was rebuilding in my house at the time an exam came up, and this is how this problem entered into my repertoire. Problem 3 is about the optimum wavefront for a ring-like structure. These sometimes cause a lot of trouble because you don't know whether to number around the periphery or to indeed go through a wave-like front. The question here is for the viewer to come up with the optimum element numbering scheme that would give the minimum RMS wavefront in compact notation. It's really not obvious how to number this, and we'll start out though with a conventional wavefront approach. So our first try will be a back and forth numbering proceeding from the top, as shown here. And we'll go 1, 2, 3, 4, 5, 6, 7, 8. We know that that would be the best for bandwidth. Now, we suspect it's also the best for wavefront. When you do this, you activate the first element, which would bring up 4 nodes. When you're done with that, none of those nodes are fully assembled in the stiffness matrix, so you don't drop any nodes from that list. Then you activate the second element, and when you're done, you can drop out the 2 that lie in between the elements 1 and 2. So these are first removed as this number 2. Then when you bring up the third element here, by now your wavefront has passed through here, you then can drop these components. The fourth element over here means the wavefront passes to here, and then you can deactivate those, and so on. As the wavefront passes through in this pattern, it ultimately sweeps through all, and it's only at the end that you can eliminate the last 4. So you have a root mean square wavefront in this compact notation, if you calculate it out, as 5.57. This certainly will beat any random numbering that you might think of. So the only other candidate would be one that would be a wave that would progress around the body, ultimately closing on itself. That would leave a couple of those nodes unsummed for a long time, and they'd remain in the computer memory a long time, but maybe it's okay. So this second numbering scheme will be analyzed here. And this time, as promised, we'll activate this first element, then we'll let the wave progress around the body and ultimately come back. And when you do the calculations, you find that you get the same RMS wavefront that we had previously, with the wave passing alternately through the elements on either side. So it turns out that both of those numbering schemes are indeed optimal. Classical plate theory